So yeah, I will talk a little bit about jetting, about dispensing, very high resolution, precise dispensing for depositing color converting materials. I will actually also say a little bit about bonding adhesives as well at the very end of the presentation. But maybe first a few words to Scrona. What are we doing? We are a company producing printheads, not just printheads, but print engines. So basically everything that goes together with the printhead that is required to integrate into third-party equipment. So we do not do equipment, we do not make inks. Our concept is that our printhead should be compatible with inks that are already on the market. And I'll tell a little bit more about that, how wide that range could be. So we are a spin-off of ETH Zurich. To underline the competence, we have at some point received the world record for printing the smallest color image. And we've also raised some money from investors to make that actually happen, because making a printhead particularly based on microfabrication, on MEMS technology, we now run our own clean room, that costs quite a bit of money. So first, let me tell you a little bit about our process, about our jetting process. It's very similar to inkjet printing. If you know inkjet printing from your home office printer, it's basically a little cartridge that has small holes inside and that pushes small liquid droplets out of that printhead, out of that nozzles. The problem really here is that we're pushing from the inside. So we're actually creating energy in the printhead where we don't need it. We need the energy at the nozzle exit, but we create it inside very fine microfluidics, and we need to bring that pressure wave to the exit of the nozzle. On that way, most of the energy is lost because the liquid resists that movement, so due to its viscosity. And that's the reason why we cannot make those openings smaller and smaller and make the droplet smaller, so that limits our resolution to approximately 50 micrometers on the substrate, or even more than that. And it also limits our viscosity that we can handle to liquids generally way below 50 centipoise actually. Now, this is actually coming quite to a halt with regards to what we can do. So obviously, printhead producers also try to make things better, but there is a limit. It's really a fundamental limit because we cannot overtake that problem. We cannot put the piezo at the exit of the nozzle because there is the liquid. And what we are doing is not just making it a bit better, but we really try to solve the underlying problem. How can we get the piezo to the exit of the nozzle? We cannot, but we can use a different actuation scheme, because we can let the liquid actuate the process by itself. So we don't need necessarily mechanical stimulus to create droplets, but there is also a possibility to create an electrical stimulus. And that's what we are doing. We're charging the fluid, we're using what is already in the fluid, which are charges, bring those charges to the surface of the liquid, and then those charges build a counterforce to the surface tension. So we fight against surface tension, not against viscosity. Viscosity is a flow parameter, so it's actually strange that it defines in an inkjet printhead that whether we print or not. In our process, it's the surface tension that counts. And that allows us now bringing that force in a focused way directly where we need it, allows us to basically project down the size of the droplets. So we use a large nozzle and we create very small droplets with it. And we can also do that with very high viscosity because, as I said, viscosity doesn't matter whether we can create a droplet or not. It just defines how fast we can do it. So now what we are really about is making a printhead that uses that concept of electrohydrodynamics, but couples it with what has made inkjet so successful in industrial environments, and that's throughput. If you're looking now at a substrate of 150 times 150 millimeters, and we want to sample that with a resolution of 5 micrometers, we count approximately 1 billion pixels. So we need to cover 1 billion pixels. That's quite a bit. So if we want to do that, and we have, let's say, 10,000 pixels, we have the technology that can process 10,000 pixels per second. Today, I've heard that number, for example, in relation with a lift process, where you eject, where you have a laser that can process 10,000 spots per second. Now, if you have that, that sounds like a lot. That is going to take you 24 hours to cover that 1 billion pixels, 900 millions. So a lot of time, not compatible with an industrial production process. So if you have that environment, you really need a technology that is not only fast, processing individual things, but you need a scalability concept. Same thing we heard today about the lift process. You're not processing 1 pixel, but you're processing multiple ones. Now, that's killing your digitality, so you're not flexible anymore.